Rutvij, we can start, I guess.
Yeah, sure. Yeah.
Okay, cool. I'll share my screen. Yeah, I hope my screen is visible. Mm,
Yep. Visible.
Okay, cool. Yeah, so in this session, Rutvij and I will talk about sparse table, LCA, which is basically lowest common ancestor, and binary lifting. So we'll define each of these terms and also some of their use cases. So yeah, first I'll talk about what is the need for the data structure sparse table. So what I've noticed is that people generally use segment trees, and and as a result, like most of them do not know about sparse tables, because most of the problems which sparse table solves can also be solved using segment trees. But generally, like in some niche problems where you need to solve queries fast, sparse tables are much more efficient than segment trees. Yeah, there are two steps to basically constructing a sparse table and then querying it. So we'll define those two steps. Uh, and yeah, then we'll show how sparse tables can be applied to calculate lowest common ancestor. And then Rutvij will talk about binary lifting. Cool. So yeah, so let's just first consider a basic problem where we are given an array which has n elements, and we have q queries where each query is defined by two integers, L and R. Using these two integers are basically the positions of some elements in the array, and we need to calculate either the minima, maxima, and or of all the elements in the array whose indices are between L and R. So yeah, if anyone has a trouble understanding what our problem statement is, then yeah, just ask speaker, please. You can also type in the chat. I'm looking at the chat as well. Okay, cool. So yeah, so like the first basic naive way would be that, like, let's say we need to calculate the, so throughout this tutorial, let's just keep our focus on the minima, and then making relevant changes for maxima and or the or operator is relatively simple. So yeah, let's say that we need to calculate the minima in the range L to R. Now this range can, at the size of this range can be at max n because the array has n elements. So the worst thing which we could do is that, like, we traverse through this entire range and we keep a variable where we keep storing the minimum. So this will take, at in worst case, this will take like O of n time per query. And because we have q queries, so the worst case which we can do to solve this problem is q into n. Okay. The second thing which we can do is that we can basically pre-compute whatever our target function is. So we are talking about the minima right now. So we can basically pre-compute the minima. So, and we can store it in a table. So basically table ij will define the minimum element for all the elements whose indices lie between I and j. So we can construct this table in O of n square time. And now when we have this table, we can basically answer each query in O of one time because we already have it stored. So yeah, so the complexity for this solution would be O of n square plus q, where n square is to compute the table and q is to answer all the queries. Now, for large n and q, neither of these methods will be sufficient, right? Because if, let's say, n is in the range 1e5, then you do not have enough memory or time to construct the table. And yeah, like if n is 1e5 and q is 1e5, then again, like the first solution fails as well. So yeah, uh, so this is where the sparse table comes into play, where we plan to answer queries in O of 1, but we need to reduce the pre-processing time, which is O of n square, right? So yeah, is there any doubt so far? If not, then I'll proceed. I'll just wait for 30 seconds and you guys can just go through the slide if you want. Cool. So yeah, I'll just start with sparse table right now. So yeah, so like let's take this example as a running example throughout our process. So this is an array. The upper row is basically the indices of the array. So the array has 8 elements, and these are the elements of the array. So first element, zeroth element has one, first index has three, and so on. Right now, let's inspire our sparse table based solution from the second method which we discussed, which had O of n square complexity. So like intuitively you can think that like the name sparse table is basically referring to the fact that we will be constructing a sparse version of the table which was consuming n square space, right? So what we propose is that let's not compute all the O of n square values. Instead, let's just store some values which satisfy the following conditions, right? So over here, like let's name our table as st. Okay, st is basically short for sparse table, right? uh, st I of j will basically store the minimum slash maximum element between indices I and j, right? But we'll store this particular value only if the length of the queried region, which is basically j minus I plus 1, is a power of 2, right? So I'll just show what all we are storing. Yeah. So for this example, let's just so basically A is the lower bound of our query and B is the upper bound of our query, right? So like this this value one is basically the minimum element in the range 0 to 0. So this is like just one element. So the answer for this is one, right? The the minimum element from range 1 to 1 is 3 because again there is just one element. The minimum element from 2 to 2 is 4 because again there is just one element. So this is how this table is constructed, right? uh, Now let's move our attention to queried regions where the length of the queried region can be 2 to the power 1, right? So if you remember that we are storing values only if the length of the queried region is a power of 2. So this part is basically storing all the values where the length of the table is 1, length of the queried region is 1. This part will store all the values where the length of the queried region is 2, and this part will store all the values where the length of the queried region is 4, which is basically 2 to the power 2, right? So let's just go through some of the values here as well. So yeah, if you notice that like a b minus a plus 1 is equal to 2 in all throughout this table, and b minus a plus 1 is 4 throughout this table, right? And let's, for sanity check, let's just go through some of these values here. So the minimum element between index 2 and 3 is basically the minimum of 4 and 8, which is 4, right? The minimum element for index between indexes 5 and 6 is basically the minimum of 1 and 4, which is 1, and so on. So yeah, let's just also go through some values in this table. So the minimum element between indices 1 and 4 is basically the minima between 3, 4, 8, and 6, which is 3, right? So these are the values which we want to store. Now, yeah, does anyone have any doubt in what sort of values we are supposed to store? I'll talk about the time and memory required to store these values after this. But if anybody is not able to understand the convention so far, then just flag me right now. Okay. So yeah, I'll assume that everyone has understood this. So yeah, so if you remember, what we had proposed was that we want to store I is like we want to store the values for I and j where j minus I plus 1 is a power of 2, right? Now, what is the maximum length which the queried region can be, right? the maximum length can be n, because that is the size of the array. But we mentioned that we only want to store the values for power of 2. So let k be the maximum power of 2, which is less than n, which would basically mean that 2 to the power k is less than equal to n, which would mean that k is less than equal to log base 2 of n, right? So for each starting index, which is I, we'll be storing, I'll just write it down. For each I, we will store at max log 2 of n values. Is this statement clear to everyone? That, like, if we fix our starting value, which is basically the leftmost part of the queried region, then because of this condition which we have implied, which is basically that we'll store stij only if the length is a power of 2, then for each I will be at max storing log n values. Is this clear to everyone? If not, then yeah, like, feel free to type in the chat or speak up. Uh, okay, cool. Then I'll just assume that everyone has understood this. So, yeah. So because, like, for each value of I, we'll be storing log of n values, and there are n values of I because we'll be storing these values for each index. So our table will at max have log n values, right? So what we have established right now is the maximum amount of memory which we would need to consume would be n log of n, right? Now, yeah, if anyone has a doubt in this, then just type in the chat. Otherwise, I'll move on to how do we achieve this in n log n time as well. Okay, cool. Yeah. So, like, let's just make a small notation change, right? So I'll first motivate why we are changing that. So let's say that the size of your array is 8, or let's just take a smaller example because it will be easier to write for me. So let's say that the size of your array is 4, and in the naive way 2, which we discussed, we'll be storing the naive way 2 is basically the one which I was talking about earlier, which is inefficient. We'll be storing the minima for the following indices, which will be zeros, 0, 0, 1, 0, 2, 0, 3, 1, 0, 1, 1, 1, 2, 1, 3, 2, 0, 2, 1, 2, 2, 3, 0, 3, 1, 2, 2, and 3, 3. So these are all the values which we'll need to store in that bad way, which was consuming of n squared space. But for sparse table, we'll be storing only these values, which is this, because the length for this is 1, this because the length for this is 2, and this because the length for this is 4, right? And we'll be storing this and this as well. We'll be storing this and this and this, right? So yeah, I hope this particular visualization is clear. So how do we store this efficiently in memory? So what I propose is that instead of defining st I comma j as the minimum element between I and j, let's redefine our definition for st I j as the minimum element in the array starting from index I up to I plus 2 to the power j minus 1. So if you notice, this particular region will have the length as 2 to the power j, right? And now we can basically, so now we can basically represent this as 0 comma 0 in our own table. We can represent this as 0 comma 1 only because uh, this has two elements. We can represent this as 0 comma 2, right? Because this basically represents a region of size 4. So that is basically 0 comma 0 plus 2 square minus 1, right? So this is like the indices which will store this particular value in our redefined convention. This will basically be replaced by 1 comma 0 because 1 is the starting index and the length of this region is 2 to the power 0, which is 1. This will be stored at 1 comma 1. This will be stored at 2 comma 0. Will be stored at 2 comma 1, and this will be stored at 3 comma 0. So again, like I'll just repeat that earlier we had defined sti comma j as the minimum element between indices I and j. Now, because we don't want to store all n square values, so if you would have used the earlier convention, then we'll be consuming space to store these values as well, even though we don't actually need to store it. So in order to like solve that, we are redefining stij as uh, the part of the array starting at index I and whose length is 2 to the power j. So yeah, so this is like a really important part to understand. So I'll just leave this on the screen for 30 seconds. So yeah, you can go through it, and yeah, just type in the chat or speak up if you have any doubts. Okay, cool. So yeah, so this is what we actually need to store. So this is basically the pre-computation step. Second step is basically how do we use this table to answer our queries. So before I move on to the logic for that, I'll just show the code for pre-computation. So this is basically clear to everyone. Yeah. Okay. So uh, is the font size fine for everyone? Okay, so I'll go ahead.
Maybe greeted by one.
Okay, cool. Yeah. Yeah, so this is basically a class, right? And this is the constructor which is taking your array as the input. So we are naming it as V. N is basically the size of the array, right? And yeah, so like if you notice, we need to calculate the logarithm of the ranges several times while querying, right? So I haven't gone to that part, but like for now, just know that we need to calculate the logarithm for several values while we are solving our queries. So what we are doing is that we are pre-computing that from beforehand. Okay. So also like we don't need the exact value of the logarithm. So yeah, I should probably have explained that before. I'll come back to this part. Okay, we don't need this right now, right? So yeah, so M is basically this table here, the ST, which I was talking about earlier, and the number of powers is basically the log of n, which I was talking there. So the length of your queried path may at max be uh, like it is basically synonymous to the 2 to the power k, which I had defined here, right? So because you need to at max store k values for each index, so we basically uh, the size of the sparse table which we need to store is basically of the size n k. So yeah, I just mention here that some power is equal to k defined, right? So this is what the size of our sparse table would be, and k is of order log n. So yeah, the size which this table will consume is n log n, right? Now, you'll notice this. This is basically initializing the part of the table which stores the minimum for length 1 only. So for our earlier example, this part is basically representing uh, minima between index I and index I plus 2 to the power 0, which is 1 minus 1, which is minima between I comma I, which is the element at index I itself, right? So this pre-computation basically corresponds to this particular table which we were talking about, right? So this is trivial, like you don't need to have anything from beforehand in order to compute this. Okay, so once we have this, now just look at this, right? Um, let's say that we want to calculate the value of I comma j. So this is basically the minimum over the segment I to I plus 2 to the power j minus 1, right? Now, what we can do is that we can break this segment into two. One can be I plus 2 to the power j minus 1, and the other can be I plus 2 to the power j minus 1 to I plus 2 to the power j minus 1. Cool. So yeah, so if you notice, the length of this particular segment is 2 to the power j minus 1, right? And the length of this particular segment is again 2 to the power j minus 1, right? So this particular value, if we want to know the minima in this range, we this will basically be represented by I comma j minus 1, and this will be represented by I plus 2 to the power j minus 1 j minus 1, right? So let's say that we know the values for the values of the sparse table for all I. uh, I'll probably rephrase it. Let's say that we know the values of the sparse table for all lengths of 2 to the power j minus 1. Then we can basically compute this, right? Because st I comma j is basically built from these two parts. And if we know the minimas of these two parts, let's say that the minima over this part is m1 and the minima over this part is m2, then this will basically be minima of m1 comma m2, right? So if we know these values, then calculating this is an O of 1 operation, right? So I'll probably just shift to the code. So I think that will be better to understand. So we already know the values for the case where the J index, which we were talking about earlier, that is 0. Now, okay, so I should have use J here so that it's clearer. Give me a second. Yeah. So like this is basically all the second indices which we're traversing about. So the first loop is basically representing the length of the queried region. So when the value of j is let's say x, then the length of the queried region would be 2 to the power j, right? Now this is basically the first index. So if we want to calculate the value of the sparse table at index I comma j, then this is basically the process which I described just right now. That you can leverage the fact that when you enter this part of the loop, you would already have calculated the value of uh, those values where the second index is j minus 1, right? So this is, and the first loop will basically be executed log n times, and the second part of the loop will be executed n times. So yeah, you'll be able to construct the entire table in n log n time and n log n space. So it is possible that this might not be very clear for some of you. So yeah, just speak up if you want me to repeat this part. This is clear to everyone? Okay. Okay, then I'll move ahead. So like now we have this table constructed,
I
right?
have a doubt.
Yeah, yeah. Go ahead, please.
Can you show the so on line 81 it says I plus 1 less than j minus 1 is less than n. Shouldn't it
Yeah.
be j minus 1, like 1 less than j minus 1 is less than, because when you put it inside the second minimum, like on line 83, I plus
Okay.
1 less than j minus 1,
Yeah.
then it should turn out to be n minus 1, no?
Nani, sorry. Can you come again?
Like in the second 83 line का second part है minimum का,
हाँ हाँ
there it should, when you add I to 1 less than j minus 1, then
हाँ
it
हाँ हाँ.
should turn out to be the maximum upper bound should be n minus 1 na.
So if I plus 1 to like I plus, I'll just write it. If I plus 2 to the power j is j minus 1 is less than n, then this will always be also less than n, right? Brackets.
Okay,
This condition is basically making sure that so yeah, so I'll tell you what this condition is making sure.
but won't 2
So
raised to j minus 1 be more precise? Won't it
online
stop?
83, online
Yes,
83.
yes, like won't it stop before maybe all the values are computed, maybe at midway, like?
You are saying that some values might be not computed in this case.
Yeah.
No, so how is that, right? So I'll just explain here. So the maximum n which you might need, that is stored in number of powers, right? Because we derived it using log base 2 of n, where n is the number of elements. Okay. So this condition is basically just to make sure that, so let's just take this example, right? I'll just put it here. So for that particular example, the value of number of powers will be 3 because n is 8. So number of powers will be 3 in that case, right? So we will need to construct a table of size 8 cross 3. But it is not necessary that we need to store all the values, because for this particular index, let's move to index 6. For index 6, we do not need to store the size of for index 6, basically we just need to store 6 comma 0 and 6 comma 1, because because 6 comma 2 is not possible, right? Because 6 comma 2 would refer to a region from index 6 to index 9, because 2 square is 4, so we are representing a region of size 4, and the array only has 8 elements, so this value might be invalid. So this condition is basically just taking care of that. You get it?
Yes, sir. 2 minutes. I'll just like think.
Sure, sure, sure. So like this, like I'm not sure if you're getting confused between the fact that like these two are not the same number. This is 2 raised to power j and then subtracting 1, and this is 2 raised to the power j minus 1.
Okay, sir. Understood. You can move on.
Sure, got it?
Yes. Yes.
Okay, okay, cool. So yeah, so this is how the sparse table is constructed. Now I'll move on to the fact that how we basically answer queries using it. Okay, so I'll just copy this here. Yeah. So let's just say that we need to answer for the minimum between indices L and R, right? Now, and let's say that R minus L plus 1 is has the length len. Okay. Now, here is what we plan to do in order to answer this query in O of one time. Let me just maybe make some blocks here. L, R. Yeah. So first, let's find the maximum power of 2. Let's call this T for now, which is such that 2 to the power T is less than equal to length, right? This is how we are defining T. Now, what I'm saying is that basically L plus 2 to the power T minus 1. This will land somewhere over here, right? L plus 2 to the power T minus 1. So the thing here to understand or probably verify is that this index will not exceed R. So I hope that is clear to everyone, because we are defining it in such a way, right? So this particular index will fall over here. Now let's define another index as L minus 2 to the power T um, or probably let's just define another index as L plus 2 to the power T. This will be exactly over here. Okay, I'll probably draw another diagram. Hmm, I think Hmm. Okay, so first let's talk about this, right? Do we know the minima in this region? We do know this from the sparse table, right? Because we have the value L comma T stored with us. So we already know the part of the sparse table in this region. Now let's define another value, which is basically R minus 2 to the power T plus 1 2R. The length of this region will be r minus 2 to the power t plus 1 minus 1, right? So this will be 2 to the power t. Wait a second, I made a mistake. There should be a minus here. So let's just define this index. Now, because we know that r minus, I'm probably making a mistake representing this here. Okay, so what I propose is that this particular index, which is r minus 2 to the power t plus 1, this will lie in some region over here, right? It might either be exactly the same as this particular index, or it might lie to the left of this particular index. So there'll be an overlap over here. I'll redraw it. This is L, this is R. L L plus 2 to the power t minus 1 will fall somewhere over here, and r minus 2 to the power t plus 1 will fall in some region over here, right? So now
There's
we, sorry.
correction.
Hello?
There's a comment in the chat.
Okay, okay. Yeah. Plus 1. Are you talking about this? Laksh? Yeah. Over here, I forgot to mention. Yeah, okay, cool. So this region also has length 2 to the power t. Now we have this value stored, right? So the value for the first region is stored in the table as LT, and the value for the second region is stored in the table as r minus 2 to the power t plus 1 t, right? We have both of these values stored. Now, basically the first value represents the minima in this particular region, and the second value basically represents the minima in this particular region, right? So now think about minima, right? Even if you calculate the minima over this part twice, it wouldn't make a difference, right? Because let's just take a smaller example where this overlap is taking place. Let's just take the example of 2 3 1 7 5 9 2, just a random example. So the minima over this part and the minima over this part, which is basically what I mean to say is that the minima of 2 comma 3 comma 1 comma 7 5 9 2 will be the same as the minima of 2 3 1 7 5 and the minima of 7 5 9 2. So this is like basically these functions are called idempotent functions. So they are defined in the following way, which is basically f of x equal to x. So like if you just think about it, uh, like what sort of functions basically satisfy these properties? One would be min, other would be max, right? If you remember earlier from the PPT, the and operator will also satisfy this because uh, 7 and like any number and with itself is basically x itself. Or operator will also satisfy that because x or x is x. So yeah, so because you have these values pre-computed, you can always basically answer all the queries in O of 1. I'll just show the code for this. So yeah, let's say that your query basically needs to find the uh, find the minima between left index and right index. This is basically L and R, which I was talking about earlier. So now what you can do is, in order to calculate the maximum index of 2, you can basically just take the integral part of the log, right? So this is what we were basically pre-computing earlier. So this is the code for that. So yeah, and this is the value of t basically, which I was talking about in the example, and this is the minima, the value which the overlapping part, right? So this is the minima of the first part, and this is the minimum of the second part, and we take the minimum of both these values. So yeah, so this is how queries are answered. So if anyone has a doubt in how queries are answered, then just speak up. I realize that like this might have slightly been unclear because I messed up the uh, convention. So yeah, anyone? Okay, cool. So yeah, if you want to check your implementation for this, then you can basically solve this problem, right? So, yeah. Um, Rutvij, should we cover LCA right now?
I mean, your choice.
Because,
I think
or should we like maybe let them implement this first and then like take LCA separately?
sure, yeah,
Because because binary
the problem
lifting
first,
is
then
not
I'll take over it.
dependent on this, right?
No, I
Yeah,
mean,
then maybe.
kind of. Actually, I mean, usually like binary lifting is usually used for LCA. There's not much uses for it. There are some.
Okay. So I just wanted like everyone to implement this before we talk about LCA.
It's a implementation. Yeah, then probably like I'd say wait right now. Like you can do
Okay.
implementation later.
Yeah. No, I
Cool
was
then I
saying that
guess.
maybe we can shift LCA to a separate session.
Separate session. Okay, I mean,
Hmm?
works with me.
Okay, cool. Then yeah, like we'll take it separately, but once everyone solves this, right? So okay. Do you want to take start binary lifting?
I mean, technically, haven't done anything separately for binary lifting. It's mostly LCA binary lifting. So yes, चालू करना होगा चालू करना होगा.
Yeah.
Like whatever prepared it's particularly LCA with binary lifting. I haven't prepared binary lifting separately anything.
Acha, cool, cool. Then I'll take LCA also. Wait. Okay. Yeah. So yeah, first I'll define what an LCA is. So like imagine that our input is basically a tree, right? And we basically need to find the LCA of two nodes n1 and n2. So this is how an LCA is defined. The LCA must be an ancestor of both n1 and n2, and LCA must be the node that among all the common ancestors of these two nodes, it must have the maximum height, right? So for example, for nodes 5 and 6, both 2 and 3, 2 and 1 are common ancestors, but the node which has the maximum height from the root is basically node 2. So the uh, LCA for 5 and 6 is 2, right? For 5 and 7, uh, the common node is basically just common ancestor is just 1, so that is by default the LCA. Let's just also take another case. So for 2 and 3, the common ancestors are 2 comma 1, but again the lowest among them is 2. So the LCA for, oh, did I write 3 here? LCA for 2 and 6 will be 2 here, right? So this is how an LCA is defined. Now, given a tree which has n nodes, and by default it has n minus 1 edges as well, by definition, we need to find the LCA for any two nodes, and we need to answer this query in O of 1, right? So given that we studied sparse tables earlier, you might have gotten the hint that we'll be using sparse tables to solve it. So before that, we, in order to reduce this problem to a sparse table, here is what we propose to do. Um, so what we need to basically construct is a Euler tree of this particular tree. Now, constructing a Euler tree is really simple. what you do is you just do a DFS on the entire tree, right? But while constructing the DFS, whenever a particular node is encountered, you push that node in an array, right? So initially, let's say that our array is empty and we start with node 1. Now, let's just choose one particular edge of 1 and let's just perform a DFS. So after traversing this edge, we reach node 2. So, okay, so while we were at node 1, we pushed node 1 to the array. We traverse this edge, we move to node 2, we'll push node 2 to the array. Now, like again, like we'll do a simple DFS. So from 2, we'll go to node 5, we'll push node 5 to this array. Now, while going back from 5 to 2, we are encountering node 2 again. So we'll again push node 2 to this array, right? Now, again, like returning back to naive DFS, we need to go to node 6 as well. So when we traverse this edge, we'll reach node 6. So we'll push node 6. We'll be going back from 6 to 2. So again, we'll encounter node 2. So we'll again push 2 to this array. From 2, we'll going back, when we go back up to perform DFS on the right side. So we'll encounter node 1 again. So we'll have 1 on this array. Um, Now moving on to this side, we'll come back through come to this edge. We'll reach node 3. We'll push node 3. We'll go back up again. We'll encounter node 1. We'll push node 1 in this array. We'll move through this particular edge. We'll encounter 4. We'll move through this edge. We'll encounter 7. We'll go back up this edge. We'll encounter 4 again. We'll push that again. We'll go back this edge and we'll push 1, right? So this is basically how a Euler tree is constructed. Um let's basically just talk about the size of this tree. So if you notice, whenever we are traversing an edge, we are adding one node, but all edges are being traversed twice, once in the forward direction and once in the other direction. So, and there are a total of n minus 1 edges. So, and because each node constructs two nodes to our Euler tree, so our array will have 2 into n minus 1 elements. But if you remember, with even before we hadn't started, we were always adding the root, right? So this particular one was added without the use of any edge. So because this will always be present, so we'll have this one extra node. So the uh, number of elements in your Euler tree will be 2n minus 2 plus 1, which will be 2n minus 1. Okay. So yeah, if anyone wants me to repeat how a Euler tree is constructed, or basically talk about why the size of the Euler tree must be this, then yeah, just speak up or type in the chat.
Don't we usually do DFS with using a visited or something? So how do we know how many times you have to visit the node? Like, do we use the size of the like 2n minus 1 to keep track of how many times you visited and then stop when it gets 2n minus 1, or like is there some other method?
Okay, so yeah, so here's what you can do, right? So because this is a tree, so you don't necessarily need to have a track of what like whether a node has been visited or not, right? So for example, in this case, I'll probably better explain it via code, but okay, delete mode, copy the entire thing. Yeah. So over here, like, just don't store anything. Like, because this is a tree, if it would have been a generic graph, then while performing DFS, you should have stored the Boolean value, which is basically represents whether a vertex has been visited or not. In this case, what you can basically do is that you can have a function void DFS, right, int s, and this is basically push s to the array, right? And then while you are traversing through the adjacency list for this particular node, you can pass this node itself to make sure that you don't visit the parent again, right? So you can do something like if, okay, so over here, like you also take the input as what is the parent of this node. So in par, right? And if parent is not the same as x, then you basically perform a DFS on that particular node. And yeah, for the sake of this Euler tree, you can push S over here again because you'll be coming back, right? So like, let me just go through a dry run on based on this graph. So like you push one, right? When you're performing a DFS for two, you basically pass 2 comma 1 to your function. Now when you are going through the adjacency list for two, you'll basically encounter three nodes, 5, 6, and 1. When you encounter one, you'll basically check over here that, oh yeah, like this particular node in my adjacency list is my own parent, so I don't need to visit it. So I just like I can basically skip that. And 5 and 6 are not my parent, so I need to perform a DFS on them. So yeah, you'll pass 2 comma 1 here. You'll pass 5 comma 2 here. You'll pass 6 comma 2 while performing a DFS on this node, and so on. Is this clear, or should I like type it on the
It is
other day?
clear. Yes, it is clear.
Got it. But like, make sure to also understand that like this approach is only valid when it's a tree and not a generic graph. Because if there is a package over here, mm, how do I get a counter case for this? 2, 6. Mm, yeah. So let's say that you basically come back to one here. Like let's say that this is no longer a tree, right? So you start from one, you come to three here, right? So for the root node, like let's just create a dummy parent, which is 1 comma minus 1, right? So you do 1 comma minus 1. Minus 1 is basically, let's say, a dummy parent of 1. Let's say you visit this particular node first, so you'll be passing 3 comma 1 here. Let's say from 3 you move on to this node, you pass 2 comma 3 here. Now when you are exploring the adjacency list for 2, you will see that node 1 is also present here, but node 2 is not a parent of node 1 because like we had decided a dummy parent for this. So in that method, when you are traversing, when your S is 2 and when you are going through its adjacency list, you will again do a DFS for 1, and this will basically never terminate. So yeah, like your tree must not, your graph must not have cycles. It must be a tree for this type of thing to work. But yeah, like you can always keep a Boolean variable.
Okay. Okay. Thank you.
Got it? Yeah.
Yes.
Okay. Yeah. So yeah. So using this now, once we have uh, this particular Euler tree constructed, what? Acha, so we must also keep track of two more things. So we need to store. We basically need to have three arrays, right? One is the Euler tree. So that is basically, let's call it Euler. Okay. As I mentioned above, this must have size 2n minus 1. Other is that you need to store the height of all the n nodes, right? So when I say height, this is basically that the height for this particular level is 1. The height for all the nodes on this level is 2, and the height for all the nodes in this level is 3, right? So again, like just while doing DFS, you can pass another variable which basically keeps track of the height. So this is another quantity which you need to keep track of. Now, one more thing which you need to keep track of is the first occurrence of a particular node in the array. So I'll just see what variable name I used in the code so that it's consistent. Mm, to understand. Yeah, okay. So let's define an array pos, and again, like this will have L elements, and pos of I is basically the first occurrence of the ith node in the Euler tree, right? So for example, uh, the value of pos for 1 will be 0, because I'll just first label this array 2, 3, 4, 5, 6, 11, 12, right? So yeah, like as you can see, this has 13 elements, which is basically 2 into 7 minus 1, right? So yeah, so the value of pos for 1 will be 0, because this is the first time 1 is occurring here. The value for node 2, so 2 is basically occurring here and here, but this is like the earliest occurrence, so you'll keep track of this value and so on and so forth, right? Now, okay, so like let's just make sure everyone understands this. If anyone has a doubt in this, then flag me. And also one more thing, like all of these values can be computed while doing the DFS itself in this particular function, right? So computing this will be O of n time only. So if anyone is not clear about this, then again, like just ask in the chat. So I'll show the code for this, but yeah, like I'll do that after I explain how LC is calculated using. Okay, cool. So now that we have this, let's just try to. So here's what we propose to calculate the LCA, right? Let's say that you have two nodes N1 and N2. Let P1 be the first occurrence of N1. So we are keeping track of that in the POS array. And P2 is the first occurrence of N2. So let's just think about all the elements. So like let's assume that P1 is less than P2 here. Okay. So if it's not, like if P1 is greater than P2, then you can just basically swap N1 and N2, because LCA of N1 and N2 is same as LCA of N2 N1, right? So without loss of generality, let's assume that P1 is less than P2. Now let's just think about what sort of nodes will be present in the positions between P1 and P2, right? So first of all, so for this example, mm, let's just take 5 and 3. Okay, for 5 and 3, okay, both of them are leaves. I'll need to take a separate thing. Hmm. I'll construct a new tree. Just wait. Yeah, 1, 2, 3, 4. Yeah, let's try to find the LCA for 3 and 10, right? 3 and 10. So when you construct the Euler tree for this, you'll basically come here. Now, this is basically the first occurrence of 3. And let's just now keep track of the nodes which will occur between the first occurrence of 3 and 10. Okay. So 4 will occur, you'll come back here. 5 will occur in that region. You'll come back to 3, you'll basically go to 2. You'll come to 6 here. You'll go back to 2, you'll come to 7, you'll come to 8, you'll come to. Okay, so like let's just go here first. You will go to 9, you'll go to 11, you'll come back up, you'll come to 8, you'll come to 10. So will it be fair to say that all the nodes between which occur in a position between P1 and P2 will will not be higher uh, than the LCA of 3 and 10. Will that be okay to say? Because like one cannot occur in this region, right? If it is not the LCA, because um, because that would mean that once you move above the LCA, you are never going to come back here. And so basically, something like 3, 1, 10 cannot occur, because that would mean that when you move back from 3 to 1, when you move from 3 to 1, then you are already going through 2. And in order to go back to 10, you'll again have to go through 2, which is like not how the Euler tree is constructed, right? So basically, what I'm proposing is that in all the nodes traverse between the first occurrences of two nodes, the node which has the lowest height, which has the maximum height, right, which is 2 in this case, which has the lowest height, which is 2 in this case, will be your LCA, right? So let's just move back to this example because we already have the values for that. Let's try to find the LCA between 5 and 3, right? So the first occurrence of 5 is here, and the first occurrence of 3 is here. So if you look at all the nodes here, right, uh, one is basically the node with the least height, right? So height for 5 is 3, height for 2 is 2, height for 6 is 3. So one is basically the node with the least height. So now, okay, so first, does anyone have a doubt in uh, why doing this gives the LCA? Why finding the first occurrence of node n1, first occurrence of node n2? This gives us two positions, and finding the node such that it occurs between P1 and P2 and has the maximum height will give the LCA. If anyone has a doubt in this, then just flag me. Uh, okay, cool. So if everyone agrees with this, then our problem is now basically reduced to performing minimum queries on the sparse table constructed on the Euler array, right? So what you can basically do is that, so I'll just go through the code right now. So this part is basically n is basically the number of nodes in the graph, q is basically the number of queries. uh, this is the part which is doing the DFS, so I'll first go through that, right? So Euler is basically the array which is storing all the elements. POS is supposed to keep track of the first occurrences. CNT is basically because like each time uh, we visit the node, one of the nodes in the tree, we basically need to increment the counter, right? So the counter is basically, yeah. So we start from zero because like this is the zeroth element of the Euler array. This is one which is the first element. So yeah, the counter is basically keeping track of that. Height is basically storing height of all the nodes. Okay. So yeah, so this is basically the DFS. Okay, so regarding the question which was asked earlier, so like the problem for which I wrote this code, this is basically storing single-sided edges. So it's a directed graph. So if it's an undirected graph, then you'll basically just send the parent over here and do what I said earlier. So right now, because we're not taking care of that, so yeah, I have not put that condition here. So yeah, so first I'm keeping track of the first occurrence, pushing that node to the Euler array, storing its height, then going through all the children of those nodes, performing DFS on those nodes. Now, after this DFS is done, I need to come back to that particular node, right? So, for example, let's say I'm on 2, I go to 3, I go to 5, I perform DFS on 5. Since it's a leaf, it returns immediately. Now I go back to 2 again. So So I need to push 2 again. So this particular statement is basically keeping track of that. And because we are adding an element to the Euler tool, so we are incrementing the counter as well. So this is how all the 3 arrays are getting computed. So if anyone has a query in that, then yeah, just flag me.
In an if there is a directed graph, then okay, but if it is an undirected graph, then won't we be given like two nodes v and u, and then we won't be given whether it is parent or which is parent, like we just be given two values, right? So how do we determine which number is closer to the root, like which is the parent of which?
No, so you'll be given the root as well. So if you are given a tree, then LC is defined only if you have a fixed root. For example, if you like draw this tree as like in this manner, 7 4 1.
Yeah, but even if root is given, it root will only
Yeah,
appear in the edges which is connected to itself, right? But say we have two phi, then it will just give two phi, right? So we need to determine key two is the parent of phi, and if it
yeah.
may even be given as phi two, so we might not assume ki phi is the parent of two. So how do we determine ki two is the parent of phi and not the other way around? Like because we know here visually ki two is closer to one because it
So
is,
so like
yeah.
for 2 and 5, we I didn't need to question exactly, like if the root is fixed, then like in such a case, I'm not really sure what you're asking.
Okay, so the question is given key one is the root, and then the
Hmm.
edges are given 1 2 1 3 1 4
Hmm.
5 2 6 2 7 4. So here
Yeah.
we don't know whether 2 is the parent of 5 or 5 is the parent of 2 without some like.
Oh, okay. So yeah. So that is like you won't know just by looking at the edges, but when you perform a DFS, since you are keeping track of the height, so like you do know that height for 2 is 2 and how height for 5 is 3. So the edge must be directed in this direction.
Okay, so we have to do a DFS with heights first, and then we have to store the parent, and then we have to do the LCA pre-computation, Euler tree pre-computation, right?
You can do it in one function only. So like should we take this offline, because I think uh, yeah,
Okay.
I'll probably just send a problem for this. Okay. But yeah, like basically you just need to keep track of the parent here and put that condition which I told. Okay.
Okay.
Okay, cool. So yeah, so this is basically how the Euler tool is constructed, and Euler tree is constructed, and yeah, like this is basically the computation of the sparse table on that tool. So this is basically calculating all the logarithm values. This is basically again like the first basic step, which is storing all the values for length of where the queried region has length 1. This is basically okay. So this is interesting. So over here, like in the sparse table, instead of storing the like the minimum element, we are storing the element with the minimum height, right? So over here, sti0 is the node with stij is the node with the minimum height in between indexes I and I plus 2 to the power j minus 1 in the Euler array, right? So, like it is possible that C1 is less than C2, but what we've got to do is we are concerned with the height. So, when we store them, when we compute the minima, we use the height function in order to do this, right? So, imagine that, like, if this were imagine if this was 7 and this was 1. So like in this particular example, I think if the number is greater, then the height is greater than equal to as well. Yeah, that holds. But like let's say that this was 7, this was 1, then that might not always hold. So like while performing queries on the sparse table, what we do is that we store the minimum node based on the height which the node has. So this is basically the pre-computation, and yeah, this is basically a function which is supposed to find the LCA for nodes n1 and n2. Um First of all, again, like these two statements are basically tracking the earliest occurrence of the nodes n1 and n2. Now it is possible that uh, n2 occurs first, so in that case, position 2 might be lesser. So in that case, like we just simply swap those values to ensure that position 1 is always smaller. And now this is like a simple sparse table thing where you basically determine the size of your query, determine the maximum value of 2, which is less than the size of your query, uh, calculate your minimum over the first splitted part of the query, calculate your minimum over the second part of the splitted part of your query. And now because this c1 and c2 might be different, because your node with the minimum height in these two parts might be different, so again you need to, so I'll just put here c1 and c2 are nodes in the tree. So now you need to again determine which of them is which one of them has the larger height. So again, like you need to make use of this height array, and yeah, this is how you return the LCA. So yeah, it's a simple function. I and j are nodes here. You use this function and you get the answer. So I like. Uh, I hope this is clear. If anyone has any doubt, then yeah, we can take it up. Uh, there is nothing in the chat as well. Okay, are segment trees and sparse table same? No. So, like they are not the same. One fundamental difference is that in segment trees you can basically update the values of your array as well, right? So, for example, let's say that over here in this array, uh, let's say I perform. Uh, okay, so the application for segment trees is basically when you might need to perform updates which are of a different type. That is, you need to also update the elements of your array. So there'll be some queries which are querying for the minima in the array, right? And then there'll be some queries which are updating the elements at different indices. And then there'll again be some queries which are querying for the minima. So now, like maybe I'll just show this with an example. Mm, let's just take an array where yeah, something like this: 2 1 3 4 5. So let's say that you perform some queries. Let's take one query as minimum in indices 0 comma 2. So minimum between indices 0 comma 2 is 2 1 3, right? So the answer for this is 1. Now let's say that you also need to take care of some update queries. So update queries will can basically be of the form that at in this index change the value from this to this. So let's just take an update query of update value at index 1 to be 10, to be 10. So this will basically change this to 10. Sorry, this remains 3 only. Yeah, this will change this to 10. Now again, like if you perform the same query, which is minimum of 0 comma 2, your answer will change, right? This time your answer should be 2. So when there are update queries between your minima queries, which is basically to say that uh, then like you might need a segment tree, because all the pre-computations which you did might become invalid when you're performing this particular update, right? Because in your pre-computations you would have stored in your sparse table you must have stored a value 0 comma 1, which is basically find the minima between indices 0 and 0 plus 2 to the power 1 minus 1. So you would have stored 1 over there. But after performing this update, the value which needs to be stored here needs to be 10. So when you're doing that, then basically your sparse table becomes inconsistent when you're performing this update. So yeah, like just to summarize, sparse tables are applicable when you are not mutating your array in between your queries. So that is what basically allows you to provide answers in O of 1. But let's say that you need to perform such updates while your minima queries or any other queries for that matter, then that is where segment trees comes into play. So yeah, but again, like the disadvantage is that in segment trees you answer such queries in log of n time. But yeah, like the advantage is that you can mutate your array while performing these queries. So yeah, that's. Um, Parth, I hope I answered your function. Can you explain why we can't use a simple DFS array to do the same thing instead of a Euler array? Okay, cool. I come to that. We'll increase the. Okay, so what do you mean by a simple DFS array? Prakul, maybe you can like type what should be a simple DFS array for this tree. Like, do you mean 1, 2, 5? Like not pushing when we are coming back to that edge. 1, 2, 5, 6, 3, 4, 7. Yeah, so like let's say that you need to calculate the LCA for 5 and 6, then you cannot be sure that uh, like for LCA you'll need to make sure that the LCA must have occurred between the first occurrence of those two nodes, right? So when you are constructing a simple DFS array, then in fact when you're constructing a simple DFS array, then the parent will always come before the children. So yeah, okay, cool. Yeah. Anyone else? Hmm. Okay. Uh, yeah, no issues. This is the first time you guys are learning. So yeah, like these are two problems which you can solve to test your implementation. Okay, and yeah, I think that's it from my end. Rutvij, you can take up binary listing.
Cool. Yeah. So just a sec. Okay, is my screen visible? Hello.
Yeah, Rutvij, it's visible.
Cool. This is weird. Okay, kind of making shit. What is it? So okay, so basically, when you're doing like, so binary, what binary listing is basically is that it kind of uses it's basically like binary jumping, also known as that. So it's basically like jump, like like it uses the fact that each can be represented as a summation of powers of two, and using that, it well, I mean. So using that, it can find the LCA in a slightly different method. So yeah, so basically what you do is, like Anmol said, calculate the Euler tour. Like you calculate the T in and T out for all the nodes in the tree, and that kind of looks like. So yeah, that kind of looks like this. So yeah, T in T out. So I'll just explain it quickly. You start from here at time equal to 0, make it T in, then time equal to 1, T in over here, and then in over here, and then you come. Then T out is the time by the time which you come out of that node and the subtree. So that's sort of Euler tool. So now then what you do is that so now what you do is you need to like you find the Euler tool. You need to get the depth of each node x in the tree, and depth is basically distance from root. Yeah, this is the depth 0, 1, 1, 2, 2, 2, 3, 3, 3, 4, 4. and then you need to find the sparse table of the tree itself. So what do you mean by that? Is that like that's actually very useful when you want to jump from one like parents like let's say it's kth parent in least possible time. So yeah, so for example, this is the tree. Then the sparse table x comma I for all of the nodes x shows the 2 raised to I parent. So basically, for node 7, sparse table 0 stores 5. For node 3, sparse table 1 stores 7 because the second parent. For node 1, sparse table 2, which stores the fourth parent, which is 1, 2, 3, 4, which is basically 5. So yeah, that kind of makes the sparse table of a tree to be this. Right? Uh, this is a tree and this is a sparse table. Yeah, so then to like computing sparse table is like it's just straightforward. You first like for all the nodes, you basically first find the parent of the node. You can do that with a single DFS, and if you sparse x comma 0 is the parent, and you can you can either calculate first to calculate the zeros column. Like you can first just calculate this column, then you can move on to the next column. Like just like you do with any sparse table, like computing any sparse table. Or what you can do is it was done over here. So we are local. So what they did is that when they reached a node, they basically like one thing like when you're doing DFS, one thing that you might notice is that uh, your the sparse table entries for all of the ancestors of that node. Like this is the node V. Then the sparse table entries for all the ancestors. Like if you can calculate them beforehand, and then once you have the ancestors so calculated, you can calculate this. So what I mean by that is, for example, if I want to calculate the sparse table entry for one, like all the entries, and let's say I'm just calculating like I have the sparse table entries for 6, 9, 7, and 5 calculated. So now the zero entry is 6. So x like db x comma like 1 comma 0 is 6. And since the sparse table entries for 6 are calculated, I can get its second value to be 9. And since the values for 9 were calculated, I can get its the next value to be 5. Like, does this make sense to you guys? So yeah, if you're doing calculate, if the tree has depth h, and that means that the deepest node has a depth of h, then you just need a floor of h plus one columns to store just sparse table, and storing any more columns would just lead to waste of space because those will all be minus ones. And minus one is basically when we store minus one if the 2 raised to r parent of node x does not exist. So since 5 is the root, all of its entries are minus 1. And to calculate the sparse table using binary listing, like for a tree, you can use this formula. So now, yeah, so the complexity for this is order n log h, where it's the depth of the tree. But in the worst case, h can go up till n, which is basically a linear chain. And in that case, so that's why we just say that it has a space complexity of order n log n. Yeah, so now, mind this. Yeah, binary list. So now so basically now we have two nodes u and v. So we without loss of generality, we assume that u is shallower than v, or depth of u is less than v. So first we need to check if u and v are if u is the ancestor of v. If not, then we can proceed. If it is the ancestor, then it's obviously the LCA. But if not, we can simply proceed. So for that, what we do is we first take some number, some variable k, assign it log h value, where it's depth of the tree, and we assign x as u. U is the shallower node. Then we keep doing this following step till k is greater than or equal to 0. So basically say that this is if the sparse table entry is -1, or it's not -1, and that the node that it stored table, if it's an ancestor, simply decrement, because the idea behind this is to take this x bring this x up, we jump it up as much as possible, as long as it is not an ancestor of as long as it's not the LCA. Basically at the end what we want is this node x, we want to jump till the direct child of the LCA. That's what we want. So if the sparse table entry is -1, or it's an ancestor of v, we simply decrement k by 1. We don't want to do that, make sense. And if it's not, then we make the jump and then we decrement k by 1. And why we decrement k by 1 is because if we don't, then it's simply jumping the k plus 1 step. We don't want to do that. We already checked for it. So yeah, finally we reach the direct child of the, and then we take its parents, and that's the LCA of node u and v. So yeah, this is all formula, a lot of formula. So I'll move on to the next example. So now this is the tree, and your u is 9 and v is 4 over here. So now first you compute the t in, t out, depth, and all that stuff. And now which first check that 9 is not the direct ancestor of 4. That is true. So we move on. We set k equal to 2 and x equal to 9. So now we get sparse table entry 9, 2 is -1, because it doesn't have a fourth parent. So we decrement k. We make it k equal to 1. Now the sparse table entry points to 5, which is the root, and which is also an answer. So we do not want to make that jump. So we again decrement it to k equal to 0. Now finally we see that the sparse table entry 9, 0 is 7, the first parent, and this is not a parent of v. So we make this jump, and now we're directly below the LCA of these two nodes. And we just take the parent and return that. That's finding LCA using binary listing. And yeah, so that's for different things. So pre-computation is basically for sparse tables. So you basically have to calculate n log h, order n is for okay. So I'll just go through this. With this Euler tool, you have to do one DFS, and to store the depth of every node. That's one DFS. You can club this too, and it's order n. Computing the sparse table, that's order n log h, where h is the height of the tree, the depth of the tree. So that's order n log h. So that these are the pre-computation steps, and in case you consider in case you consider swapping u and v based on which one is shallower, and checking checking if u is the LCA ancestor of v, these are both order of one operations, and they only need to be done once, so we don't really care about them. So we can simply say that pre-computation is order n log h plus n for now. Then the step 5. So in our case 5, yeah. Okay, that's what I said because that's outer one here. Okay, so now step 7 is this one, where we keep repeating these steps. So basically the two of these checks, like these are basically accessing sparse table entries and checking if one of them is ancestor of other one. Both of these are order one. So these are like these queries that are made are order one, and number of times that we need to make them is log h times. Uh, so yeah, this is not exactly correct, but let's fix that. So yeah, basically then so basically step 7 itself is order of log h, where h is the depth of the tree, and hence finally we can get that the query complexity is order log h and pre-computation is order n log h plus, and since the height can be n in the worst case, then we say that we have n log like order n log, like the pre-computation is order n log n, where plus n we can simply ignore the plus n, and the query complexity is order log n, and the memory complexity in this is order n log n. Not the most optimal way to find, but one thing that needs to be mentioned, like that needs to be noted, is that this calculating this sparse table for jumping to the roots, that's one of the most important things in this. So yeah, any questions regarding this? So yeah, so yeah, there's a problem regarding this. Code post is around 130 problem due to problem EL post the link. You can check this out. Anmol, are you going to do the problem that you put over here? It's not here. It's an educational stream. Check out this problem. Are you there? Hello.
Hello, yeah, Rutvij, yeah.
So are you going to do this CSS problem?
No. These are like just what I discussed. So this is like they just need to code it up.
Okay.
Yeah.
Cool. So
Like
yeah, then I guess we can.
yeah.
In that case, then I guess you guys can read this problem and 5 minutes to read it. Think about it. Then we'll discuss things. Which not a good time. दो ही लोग हैं क्या? Yes. कुल तुम लोगों को करना है क्या अभी प्रॉब्लम? नहीं तो we can end it here.
Bye.
Hello. Cool. Bye.
Yeah. Okay. Bye.
Bye.
हाँ, yeah. Rutvij, only one person is there. अच्छा, एक भी नहीं है.